Assalamu alaikum, students, and welcome to another lecture of Slate. This is me, Khawaja Yasin. Let's study chemistry. When we talk about O levels chemistry, the topic of chemical reactions is also an important one because in this chapter, we talk about three important topics. One is the rate of reaction, second is the reversible reaction and equilibrium, and thirdly, it's the redox. So, in every exam, in every paper, I can guarantee you will have questions from 15 to 20 marks in just P2 from this chapter. And likewise, there are a good number of redox MCQs in your P1s and rate and reversible reactions and equilibrium as well. So, this chapter, the best part about this chapter is there are no calculations involved. No calculations. Just like chemical energetics or moles. This is just a concept based chapter, nothing else. So, open your ears, open your eyes, let's study chemical reactions. In the first, all we need to talk about is the difference of physical and chemical reaction, students. So, what is a physical, what is a chemical reaction? When we have a physical reaction versus a chemical reaction or a chemical change. A physical change is a temporary change which can be reverted easily. It's temporary and it's easy to reverse. For instance, melting is a physical change. You melt something, you freeze something, you revert it back. You boil something, you condense something, you reverse it back. So, melting, boiling, even dissolving something in water, that's a physical change. You break the ionic bonds, the ionic lattice while dissolving. So, that is again a chemical change. Because if you're dissolving something, once you evaporate the water, you will get back your salt. So what's happening again? That's again reverting it back to the original position. So physical change is a temporary change and it's easy to reverse. Chemical change is more or less permanent, or I can say difficult to reverse. There is no such concept as that chemical change cannot be reversed because we will be studying reversible reactions in this very chapter. So they are a little more difficult to reverse. And when we talk about chemical reactions or chemical change, what do we know? New bonds are formed. In the case of chemical change, we talk about the chemical bonding. In the case of physical, we talk about intermolecular forces. Like intermolecular forces between water molecules, when they are lessened, water molecules are distant apart, they turn into steam or gas. So that's what it is all about. A very basic concept, but the most important concept of this chapter is rate of reaction. So if I have to quickly identify what is the rate of a reaction, you will simply observe something happening in front of your eyes. A reaction starts, and what do you observe later? That after some time, your reactants are going lower, the concentration of reactants is decreasing, and concentration of the products is increasing. That is the flow of reaction. But you're calculating the time as well. So rate is the change in concentration of products or reactants per unit time. And when we say that the unit of concentration is mole per dm cube, what is the unit of time? Is per second. So mole per dm cube per second, that is the unit of rate. So that is what you know about the rate of reaction. Rate can be fastened, rate can be slowed. It varies. But when we talk about the rate, it's very easy to determine that if the rate is increasing or decreasing. But before talking about that, we need to talk about something else. We need to talk about the collision theory, students. Collision theory is very important because without the concepts of collision theory, you will never be allowed to answer or describe a question of rate. You can definitely point out that if the rate is increasing or decreasing, that's not difficult. But if you have to tell them about the reason, it's the collision theory. As per the collision theory, the particles are always moving and hence colliding with each other. Now, it still won't make a difference. Just colliding with each other, that will increase the chances of reaction because there are two types of collisions. One is the unsuccessful collisions, and the other one is successful or effective collision. So, even if the molecules are just colliding with each other, it won't make a difference until or unless they are colliding with a specific amount of energy. So, unsuccessful collisions are just random collisions, but successful or effective collisions, when the particles are colliding with a specific amount of energy. Or they possess a specific amount of energy. We'll talk about that energy in a while. But before that, okay, we'll come to that later. Now, I was talking about the specific amount of energy. What is that? Students, that is the activation energy. The one we discussed while discussing the enthalpy change and the endo and exothermic reactions. That what is the activation energy? The minimum amount of energy required to start a reaction. So that is the activation energy. Or I can say the energy needed for the collisions to be successful. If the particles have energy equivalent or higher than activation energy, only then can they undergo successful or effective collisions. If they have energy lower than activation energy, no matter how many times you're going to hit your head on the wall, it won't make a difference. But If you hit your head on a wall with more effort, something will happen. But don't do that. Do not try that at home. I repeat, that was just an example. So you need a certain amount of energy, students. And that energy is activation energy. Now, when we talk about collision theory, there are four postulates of collision theory. And on the basis of that, every time, each and every time I repeat, you have to give your answer. There are four arguments. A, number of particles per unit volume. That's one. Frequency of collisions. Kinetic energy. And D is activation energy. Now, these four factors are very important. On the basis of these four factors, you every time you'll have to explain, as I said. So let's just keep these factors aside for now, and let's just talk about the factors affecting the rate of reaction. There are five factors, students. Number one is the particle size or the surface area. Now, let's just talk about that. If we have a smaller particle will have more surface area, and hence more frequency of collisions. Now, this is the point, frequency of collisions. This is something I took from the collision theory. As I said, we're going to use those points. What is a surface area? Surface area, students, is the area of contact. Now, let's look at an example, pictorial example of what happens. Look at this image. Here, I have a larger piece, larger particle size. And here I have just broken that very particle into smaller pieces. It's the same area. The area is still the same. You just add the smaller particles together. But the surface area is different. Surface area is the area of contact. Let's imagine I put that in water. Water will attack from this side, from this side, from this side, from this side. That's it. But when we talk about these smaller particles, water from this side, this. Now more of the area is exposed for water to react. Similar particle, but broken down into smaller pieces. So this is a smaller particle size, but more surface area. And by more surface area, we mean more water molecules can come towards it, more of them can collide. So more frequency of collisions. Here, we'll only have collisions here, or here. In this case, I will have collisions from all the directions, students. from every side, we'll get the collisions. So more frequency of collisions, hence more chances of successful collisions. And if the chances of successful collisions have increased, hence more rate of reaction. So the point is, if you have a smaller particle size, more surface area. More surface area, more frequency of collision. More frequency, more chances of successful or effective collisions, hence more rate. In your exam, powder always has the largest surface area as compared to, you can get various things as compared to a lump or ribbon or a stone or a marble, anything. So particle powder is always the smallest one. So particle size is inversely proportional to rate. Smaller the particle size, more the rate. And we took one factor from the collision theory, frequency of collisions. So in the case of particle size, I will talk about the frequency of collisions. And not only that, this is the same volume. How many particles do I see? One. Same volume, same area. How many particles do I see? 8. You see that? So this also has more number of particles per unit volume. So the number of particles has also increased. And that will also increase the rate. As per the collision theory, these two factors are at play. Frequency of collisions have increased, number of particles per unit volume has increased by the particle size. So in both the cases, we will talk about a particle size. Now, let's talk about the very other factor. The other factor is concentration. Now, when we talk about concentration, there are two cases. Either you have a lesser concentration or you have a higher concentration. So, in less concentration, you see lesser particles. In higher concentration, you see higher particles. It's as simple as that. So, where will you have more collisions? In the high or less concentration? Definitely in the case of high concentration. So, higher the concentration, now, higher the concentration, more number of particles per unit volume. As you can see that. And therefore, more frequency of collisions. Hence, more rate. Lower the concentration, lesser number of particles per unit volume, hence lesser frequency and lesser rate. So we again use the very 2 points in the case of concentration as well. So particle size is 1, concentration is 1. Next, we talk about pressure. Now in the case of pressure, when pressure is increased, now if this is my movable container, it has a fixed volume. If I increase the pressure, volume is getting decreased, right? The volume is decreased. If I increase the pressure, the volume is decreased. And let's talk about this very factor. In the case of particle size, number of particles were increased. In the case of concentration, again, number of particles were increased per unit volume. But in the case of pressure, we are not changing the number of particles. Rather, we are decreasing the volume. So again, if we decrease the volume, there will be more number of particles, hence more number of particles per unit volume. And therefore, increased frequency and increased rate. So again, in these three parts, we talked about the very first two things, which was the frequency of collisions and number of particles per unit volume. But now let's talk about the other factors. The other factors, D is temperature. Now, temperature has a double effect. A, since particles are in motion, what will happen? Temperature will increase the kinetic energy of particles. Definitely. And they will move faster. And if they are moving faster, you can see it here. Low temperature, high. Now they are going to move faster. So in this case, they will definitely move faster, and frequency of collisions will be increased. Now, that's not the only thing. That was one thing. Frequency of collisions have increased. But remember one thing, I would write it here. Temperature has no effect on activation energy. It has no effect on activation energy. But look at a few particles. Like if I would say, this is my activation energy at low temperature. And I would say, these are my particles. Now, only the particles having activation energy higher than activation energy will undergo successful collisions. Only these particles can undergo successful collisions, right? Because they have energy higher than activation energy. But if I increase the temperature, now more particles will have energy higher than activation energy. Catalyst temperature has not changed the activation energy. Activation energy is still there at the same level. But as it has increased the kinetic energy, more particles will now have energy higher than activation energy. Now, in this case, all the particles having energy higher than activation energy, they can undergo collisions. So at higher temperature, more particles will have energy higher than activation energy. And if more particles have energy higher than activation energy, what will happen? That would lead to more successful collisions. Now, at higher temperature, there will be more successful collisions. Now, this is the only time we're talking about more successful collisions. Look at this. At low temperature, they have a particular movement. But here, at the higher temperature, they're moving faster. But now they have a sufficient energy to react and form the products. So they have energy higher than activation energy this time. So at higher temperature, more successful collisions, hence more rate of reaction. So temperature increases the kinetic energy, more frequency of collisions. And also it increases the energy of particles. So more collisions will be successful this time. The temperature has a double effect. And last factor is catalyst. Now what is a catalyst? A species that speeds up a chemical reaction without getting used up. It is used. It is a part of the reaction, but it is not used up. By used up, we mean the amount has lessened or ended. The amount is still the same at the end of the reaction. So it is not used up without getting used up or chemically changed during a reaction. So it's neither used up nor chemically changed. But how does it increases the rate? Two ways. It increases the rate of reaction by providing an alternate route to the reaction. We'll just look at that. And mainly by lowering the activation energy. Now, temperature had no effect on activation energy. Catalyst only and only has an effect on activation energy. No effect on the number of particles, no effect on the speed of particles. It only lowers the activation energy. So, if you recall from enthalpy, or you can see the previous lecture on our page, if this was the activation energy of a normal reaction, after using catalyst, it will be lowered like this. This is EA with catalyst. So catalyst increases by just lowering the activation energy. So in the case of catalyst, we'll just be talking about this point of activation energy. For temperature, temperature increase the kinetic energy, increase the frequency, and more particles at energy higher than activation energy. But in the case of catalyst, we'll only talk about activation energy. So as I said, all 4 points of collision theory are important when you talk about the rate. So that is what we know. And remember, powdered catalyst is always better. Why? More surface area. That's it. So I can explain it to you in another way. We will talk about the similar graph from this one. So this was my reaction without any catalyst. Now This is the energy on y-axis, and I've used a catalyst. So the activation energy is lowered. So this is activation energy with catalyst. So at this time, even this and this particle can also undergo successful collisions because the standard has come lower. Now, lesser energy particles can also undergo successful collisions. So so a catalyst increases the rate by lowering the activation energy, and more particles can undergo successful collisions. Now, all these five factors are used in a graph. A very basic graph. It's always the same. Now, we have time here and we have the amount of product on Y. It can be mass, it can be volume, or anything. It can be volume of a gas. There are various examples. So, know one thing, at time zero, the amount of product is zero. So, gradually, know one thing before I talk about the rate. Rate only increases the speed, right? It does not have an impact on the amount. Amount will always be the same. Amount for amount, we need to change the quantity of the reactants. We'll talk about that example. Amount can be changed, but for that we need a different thing. So gradually the reaction starts proceeding in this way. But if there is only a specific amount of product to be formed, for instance, this is the amount of product. That's how the graph would look like in normal case. But if I increase the rate, so in a lesser time, for instance, 5 seconds, 10 seconds, 15, 20. Now it took them 15 seconds to attain the amount of product, as you can see. But if I increase the rate, I will get this very amount of product quickly. So we will have a steeper slope. And as I said, amount will still be the same. We will not go more than this amount. Amount is still the same. The only difference is now we have attained our product in almost 7 to 8 seconds. So now we have achieved our goal in a quicker way. So, what would increase the rate? So, this would be the graph. This would be the steepness in the case of all five things. Smaller particle, high concentration, high pressure, more temperature, and catalyst. So, it would be the same in these cases. But what if I increase the particle size from this normal blue line? I decrease the concentration, I decrease the pressure, I decrease the temperature, I remove the catalyst. The reaction will slow down. So it may go this way. It will have a reverse effect this time. The amount will be the same, but the time to attain the product has increased. So this is slower rate. So these are the types of graphs that you will always see. Just one past paper example, for instance, 5 gram of magnesium ribbon reacts with 10 gram of magnesium ribbon reacts with excess HCl and H2 is produced. This is reaction 1. Reaction 2, 5 gram of magnesium powder. So know one thing. In this case, there are two differences. Ribbon and powder. We know in the case of ribbon and powder, powder has the faster reaction. But there is also one more difference. We have more amount of reactant in the case of ribbon and less amount of reactant. So more the reactant, more product will be formed. Less the reactant, less will be formed. So reaction 1, where we have 10 gram of magnesium ribbon, it's ribbon, so reaction will be slow. But 10 gram, so more amount, volume of hydrogen is more. It's a slow reaction, but more volume. So this is reaction 1. But here we have 5 gram, lesser product, but powder, so quickly, faster rate. In this case, it will be a faster reaction, but half the product will be formed. So these are the types of questions that you see in the exam. Last thing about this topic is how to investigate rate through experimental procedures. That's an important question that has been a part of your P1, that has been a part of your P2s, and especially in P4s. So rate, when we have to investigate the rate, there are two important methods. One is the loss of mass method, and the other is disappearing cross method. Now these two are altogether opposite ones. Let's look at the picture, the diagrams and the images regarding both of them. First, let's talk about disappearing cross. Ignore that we're talking about sodium disulfate here. Let's recall solubility rules, and I place a paper and I put a cross on it, and I just have a solution. It's a transparent solution, as you can see. And for instance, this transparent solution is a sodium chloride solution. And I'm going to add a silver nitrate solution. So what will happen? As you've added silver nitrate, this will form AgCl plus NaNO3 sodium nitrate. Remember, silver nitrate is a solid. It's a precipitate. So gradually, you will start the time, and gradually the precipitate of silver chloride will form. Precipitate are insoluble. They will make the mixture cloudy, and gradually with time, disappearing cross. The cross will start disappearing here. What will happen? It was a transparent solution here where I could see the X. Now I cannot see the X. How do I see that? From the view from the top. So here you can see the difference. You will start the time here and then you'll stop the time. When you stop, look, when the cross disappears, this is one way to investigate the rate. Here, from transparent, we move towards insoluble product. From transparent to insoluble, that's disappearing cross. Loss of mass method, that is something you've talked about mostly. If I add a solid calcium carbonate in a solution, obviously calcium carbonate will have a mass, it's a solid. But here I will have, for instance, HCl. So calcium carbonate plus HCl will form calcium chloride, which is an aqueous solution, plus carbon dioxide plus water. So the solid calcium carbonate is disappearing. This is the loss of mass method. Here we have taken the mass of the mixture, and when we add acid, we see that how the calcium carbonate is losing the mass because it's converting into a gas, and gas is going and being collected in this apparatus. So the mass is decreasing, and this is the loss of mass method. How to finalize which method to choose? In the loss of mass method, we started off with an insoluble product and we dissolved it. It lost its mass. And in the case of disappearing cross, we produced an insoluble salt. So, students, that's all for the rate of reaction, where we talked about the collision theory, where we talked about the factors of the rate, and where we talked about the graph. And lastly, we talked about the methods of investigation. So, that is rate. In the next video, we'll talk about the reversible reaction and equilibrium, something that confuses the most of you. So, thank you so much for being here with me. Allah Hafiz.